Imagine waking up to headlines. All the world's glaciers melted last night. The image is dramatic. Ice gone, rivers running wild, mountains denuded. It is also an extreme thought experiment. What would actually happen if every glacier on Earth released its ice all at once? The short answer: cascading and uneven consequences, sudden floods in some places, an immediate but partial rise in sea level, abrupt shifts in freshwater supply for millions, and long-term changes to ocean circulation and climate feedbacks. In this episode, we'll trace the physics and the social impacts, step by step, and link each claim to the scientific evidence. Start with quantities. How much water is locked in glaciers today? Mountain glaciers and small ice caps, not including the Greenland and Antarctic ice sheets, contain a significant volume of fresh water that is already contributing to sea level rise. Current observational assessments show that glaciers worldwide have been losing mass at an accelerating rate, and that glacier melt has been responsible for a substantial fraction of observed sea level rise in recent decades. Those losses added measurable millimeters to global mean sea level this century and represent trillions of tons of water that would, if released, end up in the ocean. The World Glacier Monitoring Service and the IPCC summarize these changes and the basic numbers. Now, imagine that volume dumped into the ocean overnight. Global mean sea level would rise by a value equal to the sea level equivalent of all glaciers, plus any contribution from ice sheets. By itself, small glaciers and ice caps contribute on the order of decimeters of potential long-term sea level rise if fully melted. But if all glaciers vanished instantly, the immediate sea level jump would be substantial and regionally variable, leading to widespread coastal inundation, shoreline retreat, and loss of low-lying lands. Coastal cities and infrastructure would face sudden flooding, and storm surge events would become more destructive because they start from a higher baseline. IPCC assessments and glacier volume studies give the methods to calculate these equivalents and their implications for coasts. But effects would not be uniform. Some regions would experience catastrophic floods from sudden downstream release. Think glacial lake outburst floods or GLOFs, but on a global scale. Glaciarized mountain drainage systems often feed reservoirs, hydroelectric dams, and agricultural irrigation. If the upstream ice buffer disappeared overnight, many mountain watersheds would see an initial pulse, extreme flood flows that could destroy infrastructure, erode soils, and deposit sediment far downstream. The literature on GLOFs and accelerating glacier melt warns that abrupt lake draining and dam failures are an outsized near-term hazard when ice retreats rapidly. The hydrological consequences are complicated by timescales. In many mountain regions, glaciers act as natural water storage. They release melt during dry seasons and sustain river flow when monsoon or snowpack is low. If glaciers melted instantly, you'd get a short period of unusually high runoff, flooding, followed by a long-term deficit. Rivers that used to be fed by summer melt would have far less base flow in late summer and fall. That is a direct threat to water security for tens of millions of people who rely on glacier-fed rivers for drinking water, irrigation, and hydropower. The IPCC's special report on oceans and cryosphere and multiple basin studies show these seasonal shifts and their social implications. Agriculture and hydropower depend on predictable seasonal flows. Regions such as the Himalaya, Andes, and parts of Central Asia and the Andes rely heavily on meltwater to smooth seasonal variability. An overnight melt would mean immediate downstream floods that damage crops and infrastructure, and then, as glaciers no longer exist to feed rivers, chronic summer water shortages that reduce harvests and hydropower generation for years to come. Economies that depend on irrigation timing and dam operations would suffer, and markets and food prices would react. Recent studies and reviews document projected reductions in glacier runoff in many basins and the knock-on economic impacts. There's also an ecological angle. Freshwater ecosystems near glacier outlets are adapted to cold, sediment-rich flows. Abrupt melt pulses flush sediments, reshape riverbeds, and can extirpate sensitive species, aquatic insects, juvenile fish, and specialized algae, while other opportunistic species colonize the disturbed streams. Coastal ecosystems would also feel the change. Sudden pulses of cold, fresh water near river mouths could temporarily alter salinity, nutrient flows, and local fisheries. Paradoxically, some places could see temporary boon, newly accessible stream habitat for certain salmonids where glaciers retreat. But the overall ecological disruption would be severe and uneven. Scientific monitoring shows both positive and negative ecosystem responses to accelerated glacier retreat. We also must consider geomorphology and hazards. Sediment stored in and beneath glaciers would be mobilized. Mountainsides destabilized as ice that buttressed slopes vanishes. Permafrost and frozen talus can thaw and slump, increasing landslide risk, debris flows, and infrastructure damage. The IPCC and mountain hazard literature record increased frequency and magnitude of slope failures and show that retreating ice destabilizes previously supported terrain. On a planetary scale, there are feedbacks to climate. When reflective ice cover disappears, the planetary albedo, the fraction of incoming solar radiation reflected back to space, decreases. Less reflection means more solar energy absorbed, amplifying local and regional warming. Melting glaciers also expose darker rock and soil, accelerating local warming further. That albedo feedback is one reason polar and alpine regions warm faster than the global average. In addition, sudden freshwater input to the ocean affects salinity and buoyancy-driven circulation. Large freshwater pulses into subpolar regions can slow elements of thermohaline circulation, with possible knock-on effects on regional climate patterns, storm tracks, and precipitation. IPCC assessments describe these mechanisms and their potential to modify regional climates when cryosphere mass declines rapidly. Another global worry: permafrost and greenhouse gas feedbacks. Rapid regional warming and melt destabilize permafrost in nearby Arctic and subarctic regions. Thawing permafrost releases methane and CO2 from formerly frozen organic matter, a positive feedback that amplifies global warming. Scientific reviews of permafrost carbon dynamics emphasize that abrupt warming and thaw can accelerate greenhouse gas emissions, compounding the initial climate forcing and making long-term recovery harder. Human consequences would be profound. Short-term, emergency response overwhelmed by floods, gloughs, dam failures, and rapid displacement. Long-term, reduced hydropower and irrigation, food insecurity, migration from drought-prone mountain-fed basins, and coastal loss from sea level rise. Economic costs would be enormous, from destroyed infrastructure to lost agricultural productivity and resettlement costs, and would hit vulnerable communities hardest. Reports on economic impacts of glacier loss and regional assessments highlight the scale of potential losses and the inequality of impacts. So, what would be survivable and what would be irreversible? Some engineering solutions, emergency dams, sediment basins, and flood defenses, can mitigate immediate floods, and improved water management can stretch limited water supplies. But you cannot instantly replace the long-term water storage function of thousands of mountain glaciers. Rebuilding that storage would require major infrastructure, large reservoirs, built at enormous cost and with significant ecological trade-offs. Some losses, biodiversity shifts, landscape reconfiguration, and the cultural losses tied to mountain glaciers, would be effectively permanent on human timescales. Finally, what does science say about the plausibility of an overnight melt? The physics and energy balance are simple. To melt the global glacier inventory instantly would require an astronomical amount of heat delivered in a single night. There is no credible natural mechanism, no volcanic eruption, no solar pulse, no meteor that could in practice deliver that energy uniformly worldwide and melt all glacial ice in one night. Observations show accelerated melt on multi-year to decadal scales, not instantaneous global disappearance. However, thinking about an extreme hypothetical like this helps us understand vulnerabilities, the near-term flood hazards, the long-term water deficits, the ecosystem and economic impacts, and the feedbacks that would amplify warming. In short, instant melt is physically implausible, but rapid, regionally concentrated melting is both plausible and already happening in many places. And its consequences are exactly the kinds we describe. If you want to dig deeper, the IPCC Special Report on Oceans and Cryosphere and the World Glacier Monitoring Service provide authoritative data and scenarios, and there is a growing literature on glacial hazards, gel-offs, and permafrost carbon feedbacks. Understanding these pathways helps societies prioritize adaptation, early warning and monitoring for GLOFs, investments in water storage and diversified supply, protection of downstream ecosystems, and of course, aggressive climate mitigation to reduce the rate of ice loss. If this thought experiment made you think differently about water, climate and risk, subscribe. We'll keep turning dramatic what-ifs into careful, evidence-first explanations so you can tell the difference between plausible danger and sensational claims. Thanks for watching.